Hi, everybody. These are our directions for our shadow plots and directions activity. Excuse me. And what everybody should currently have right now, everybody should have their 3 season shadow plots. Here they are. This would, of course, be winter. Everybody should have a line connecting their points on their shadow plot. And everybody should have found the local noon line, which goes to the shortest shadow. And you can see on winter, the shortest shadow is still not very short. And it went from the gnomon to here because the sun, even at its highest point, doesn't come up very high in the winter, which means we're going to have long shadows all day, but we still have a shortest shadow. And it goes right through here. And it was odd because this one actually went through the time noon, which is unusual. And of course, I asked you guys, and if you haven't done this, you want to for today, to actually draw the line from below the gnomon through the gnomon through the line up here, even though the actual shadow itself only went from there to there. At any rate, that's what everybody should have done and be looking at right now. Now, the activity that we just got done with in class, we took a globe. We took a globe and we put a gnomon on the globe. And when we put the gnomon on the globe, we rotated the globe and we found out that the shadow the gnomon makes works just like on a real shadow plot where it goes from longer shadows to a shortest shadow back to longer shadows like it does on all our shadow plots. But we found out that shortest shadow consistently did something. And you can see it on the picture here. It consistently always lined up with a line of longitude. And the reason that's important is because of where all these lines of longitude end up. But on any place on the earth, when you find the shortest shadow, you're going to be finding it's going to line up perfectly with a line of longitude. And those longitude lines all end up at the same place. You can see this follows the longitude line up. They all end up at the North Pole. So that means that the shortest shadow of the day doesn't only tell us the highest point of the sun in our area or anywhere above the Tropic of Cancer rather, it's going to go and point right at the North Pole. Now that's a very important thing because we call that true north, which is exactly what it is. It's a true North Pole indicator. So I'm going to show you why that is an important thing. But before we do that, let's go back to our shadow plots. Remember what we just found. We found out that this local noon shortest shadow always points north. So now our shadow plots are giving us a direction. And this, of course, would be south. Now, it's really important that this is what's called true north. Well, what does that mean? Well, guys, compasses, which people have used to navigate for centuries, are actually kind of hard to use. And that's because if you have the earth with a line going through its axis, that is north and that is south. But when you use a compass and it tells you you're going north, it's not really pointing at that. And that's what makes them difficult to use. It's actually pointing at a spot over here called magnetic north, which is where the magnetic North Pole is, but it's not at the real North Pole. And the final thing that makes compasses really difficult to use is you have to figure out what's called the declination. And the reason is that as you move up in latitude, I'll draw a line right here. As you move up in latitude, the angle between magnetic north and true north right here, it actually changes every time you move up a latitude line. Every time. And you have to use a declination table so that you can compensate for that so that your compass is really pointing you where you think it is. And it also requires to use it effectively that you, one, have a declination table, and two, have at least a pretty good idea of what line of latitude you're on. Well, not with the shadow plot. Shadow plots point directly at the true North Pole. And if you can make one of these, you can actually look at a regular compass, find the declination and use that declination to figure out what latitude line you are on, working in reverse. So all the problems with using a magnetic compass, we solve with using a shadow plot compass. So these have been really helpful throughout history in helping people navigate and map. So the other thing we can do on this, now that we've got a north line and a south line, is I can come here and notice I'm going right at where my gnomon was, and I'm putting that right on the middle of my protractor. And I'm just going to make a little mark right here. And now I can make another line. Notice everything's working through the gnomon. Now I've got a compass rose, west and east. Now I want to use this to think about where the sun was at certain times of the day. We know we can't start our shadow plots right at sun up and sundown, but we know that they follow the trend of the line, and sun up was somewhere up here, which doesn't change really drastically in terms of the gnomon. Sundown was somewhere way out here. And that means that sunup, if we remember that light travels in a straight line and that all shadows are opposite pointers of the sun, that means that the sun was somewhere down in this area of the sky, give or take just a very small amount, when it rose. It was in the southeast portion of the sky. Conversely, this shadow was somewhere out here at sundown. We line this up with the gnomon, and that means the sun was somewhere, roughly, give or take a few millimeters, in this portion of the sky at sundown. So now we've got a couple of answers for our ecliptic. We now know that at sunrise over here, the sun was in the southeast portion of the sky. That's our sun up direction of the sun. We also know that at sundown, it was in the southwest portion of the sky. So it set southwest, and the middle day at local noon. Remember, the local noon shadow does that, and the shadow is the opposite pointer of the sun. The sun was directly south of us because the shadow was pointing directly north. So we now have some directions for the sun on our ecliptic in the winter, first day of winter, or whenever this was really close to the first day of winter. This was rose in the southeast sky, came up mid to and was in the southern sky directly in midday or at local noon, set in the southwest sky. And we also know that it didn't go up very far. So what you're going to want to do on all three of your seasonal shadow plots now is add this compass rose and write down the directions the sun were in at the beginning of the day, midday, and at the end of the day. And you can do that just by looking at the shadow plot like we just did here. The tricky one on here, do this one last. The tricky one on here is spring, fall. And it's just, and we'll get to why that is, but definitely do what we just did on winter right there. Do that same thing for summer. Draw a little ecliptic, show where the sun was at sunrise, local noon, and sunset. And then we can talk about, once you've got those, then we can talk about spring and fall. So anyway, that's your task. Thanks for watching.